Welcome, everyone. No, please don't go. Formal verification is interesting, I swear. All right, no worries. Well, welcome, everyone, and thank you for showing up to Beyond Threat Modeling, Formal Verification for Cloud-Native Infrastructure. Professor Viganò and I, we will introduce ourselves momentarily. For now, we would like to thank you for showing up after lunch, as well as FINOS for organizing another amazing open sourcing finance forum here in London. Super, so I'll start. Francesco, Head of Technical Solutions at ControlPlane. I wasted my youth in dusty data centers for government institutions, as well as aerospace and defense organizations. That's where I start appreciating the limitations of traditional risk assessment and threat modeling techniques, especially when we are talking about safety-critical and business-critical systems. ControlPlane, we are headquartered in London, but we operate globally with presence, let's say, 5 eyes countries. We are around 60 people. We are fully bootstrapped and independent. So our services is really about bringing value to customers, not about selling one solution. Unless we are talking about Enterprise for Flux, because it's our flagship product supporting CNCF Flux CD. Welcome, Matt and Liz. So ControlPlane, our methodology is always to tackle cloud-native challenges for our regulated customer base. We typically start with a threat model. We then help designing, building, and then assuring systems. We do that for any permutation of the systems you see below. Kubernetes, as I said, our enterprise distribution of Flux CD. We are large advocates of GitOps-driven DevSecOps. We very much like to design and secure AI MLOps systems, and also to secure the supply chain of regulated industries, especially in the open source ingestion. And then, sir?
Yes, well, not sir, come on. Hi, I'm Luca Viganò. I am responsible for his wasted youth. I was his professor when he was at the University of Verona, and then, luck has it, we met again in London after many, many years. So I'm a professor at King's College, London, so just across the river and a little bit long, where I had the cybersecurity group. And that is actually one of the key takeaways of today's talk. So King's, like many other universities, has a cybersecurity group. We have about 12 people in our team, 12 permanent staff, plus postdocs and PhD students working on different facets of cybersecurity, ranging from socio-technical cybersecurity to AI for security and security of AI, and to people like me who are formal methodists. That's me there at the center. I work on, well, cybersecurity, cyber in parentheses, because there are many different flavors. You don't necessarily need to be online. It can just be information security. I work on AI and logic, old-fashioned AI. I'm old. Automated reasoning, not necessarily machine learning, but also machine learning for security, and logic, which is fundamental for the talk today, because we're going to talk about formal methods, so rigorous ways based on mathematical logic. Obviously, there are connections with software engineering, and I'm not going to talk about it, but I'm also very, very interested in connections with the arts, and how arts can be used to explain security, and vice versa, the role that security plays in the arts.
Thank you very much. So, spoiler alert, is it okay to leave with a headache today and a desire for a pint? Because the agenda is quite busy and it covers mathematical concepts, but articulated in a way that hopefully most of you can understand.
No formulas. No formulas.
Okay, no formulas. Only concept, I swear. So we will start from something very, very familiar with everyone, hopefully, threat modeling, especially how threat modeling is adopted in regulated industries like FSIs. We will then explain the reasons, the limitations that brought us to put together this initiative, the Knowledge Transfer Partnership. We will explain what that is. We'll then give you an overview of what formal methods are. And then we'll bring a case study, is actually what we are doing, and is about assuring Kubernetes beyond what threat modeling, traditional threat modeling can do, and why that may be very relevant for security-minded and risk-averse organizations like FSIs. Then we'll close, of course, with an honorable mention of a control set available out there to harden Kubernetes deployments after key unknown risks are flagged by our, I can now say prototype, Mario. Very well, so I want to start from this quote, very famous quote. The only truly secure system is one that is powered off, cast in a block of concrete and sealed in a lead-lined room with armed guards. That's Gene Spafford. That's a very famous quote. In fact, the quote continues. He says, and even then, I have my doubts. So, well, regardless, my question to you is, how useful and usable such a system would be? Well, not very much, because unfortunately, connectivity of systems is a hard requirement. And with connectivity comes exposure. So, systems are required to be interconnected to be actually useful. We use them every day. What we have to manage is the exposure of such systems in this interconnected network. So we had to find, historically, security models and associated security controls to de-risk access to interconnected systems, both from other systems and, unfortunately, from humans. And we came up with a bunch of very, very cool stuff like air-gap networks, no connectivity whatsoever, really advanced security controls. But then what happens is that this guy arrives, and I hope you know the movie. So the most secure air-gap system in the world that is still an unknown threat that can exploit a weakness in the way the system is designed or configured or deployed or operated. So what is left for us to do? What we do at ControlPlane, we get extremely good at threat modeling. So what we want to do at the end of a threat model exercise is fundamentally to derive threats, mitigation strategies, and security requirements for our systems. And we want to use them to secure the way we design, deploy, and operate systems at scale. So far, no rocket science. Very well. Unfortunately, in traditional threat modeling techniques, there are some limitations. AKA, our methodologies and our output is only as good as the threats you can imagine. So the unseen weaknesses remain unaddressed. And that's when Tom Cruise comes down from the ceiling and can hack in the system. Is unknown threats coming from unseen weaknesses. So it's very hard to explore complex interactions between system components. In Kubernetes, you have like a container orchestration, sidecar network policies, a lot of moving parts. And as we all know, attackers can always innovate faster than we can model and therefore secure. Why this is particularly bad for FSIs? I'm going to say to you guys, because you're most likely from FSIs. So financial systems are considered critical national infrastructure. Failure of such systems is fundamentally an operational, a financial, reputational, and regulatory impact to the organization. And unknown unknowns are actually the true danger. As I said, especially for risk-averse organizations. So there must be something better we can do. And as a good engineer, I ask myself, who can I talk to? Of course, the answer is academia. So Professor Viganò and I we go back a long time. A couple of years ago, I reached out saying, this is the issue. We can secure systems for our customers up to a point. And that unknown is where the residual risk lies, and that's sometimes unacceptable. So we came up, actually, he suggested we should apply for something called Knowledge Transfer Partnership, or KTP. That is a program sponsored by UKRI via Innovate UK, so is public sector UK sponsored. Originally was ControlPlane, King's College, and then one of his team left King's to join UCL, or University College of London, and we extended the partnership to UCL as well. It's a 2-year project, and again, it has a very, very concrete application, and it's about solving modern industry challenges via support from the academia. So we have that sort of field expertise. We threat model daily for regulated customers. We see a limitation, we see a gap. That's when the academia can bring a wealth of technical knowledge trying to address those gaps. It's applied research. Inception of the idea, this happened last year. We're now developing a prototype. Marco here in the audience is the postdoc working at ControlPlane. Mario, working at ControlPlane, King's. And then prototype is almost ready. And then as part of the KTP, there is a strong commercial angle. they like to see a commercial roadmap at the end. How can end-user organizations consume this tool at that point? And we, of course, started from Kubernetes, the most awesome platform available to us. Real quick plan is starting from Kube, deemed as a business-critical system from FSIs. We formalize the system. We'll show you later how. We define the security guarantees the system must preserve. We then feed the formalized system to an automated reasoner. They can also assess the evolution of the system in time and return, hopefully, all the states of insecurity. And after that, the tool, beyond the prototype, will also translate this gibberish, which we'll show you later, into something that can be consumed by humans, the threat modelers, so supporting the professionals on their everyday job. And with that, let's see what formal methods are.
So, as we promised, no formulas, but what are formal methods? So formal methods are, in a nutshell, they're rigorous techniques based on mathematical logic. I mean, you might know inferences from high school, perhaps, like things like, all men are mortal, Socrates is mortal, and Socrates is a man, and therefore Socrates is mortal. That is one of the very first inferences that you learn. Basically, there are ways in which we can formalize reasoning. Okay? And they are fundamental precisely for what Francesco was mentioning, because humans are actually pretty good at threat modeling and finding attacks. But they are not going to model everything, and they're not going to find every attack. Whereas an approach that is based on mathematical logic, that is based on formal methods, does give us the opportunity of modeling such a large search space that we can be very confident. You never have 100% guarantee, and I'll explain in a moment now, but you can be very confident that either you have found an attack, and there you can be sure that it is an attack, or that there are no attacks. Now, this is the only part where I'm going to be slightly technical. Security is, in our terminology, an undecidable problem. We cannot decide whether a system is secure or not in general. Or to put it using the words of Alan Turing, whose birthday was yesterday or today, I don't remember. Yes, so we cannot write a program that will always terminate with a yes or no answer to the question, is a system secure? Okay. It's impossible. And the intuitive reason for that is very, very simple. In the case of security, we're looking at threats. Threats originate from attackers. We want to consider the strongest possible attackers, because otherwise we are only securing our system with respect to a non-realistic attacker. Well, the strongest possible attacker can always do something else. So your tool will never terminate, because there is always something else that you can check. But in many, many cases, like in the work that we have been doing, you can actually reduce the problem to either a finite problem and then you can check it, or you can reduce it to proving security under certain guarantees. And then these guarantees will be checked by humans, will be checked by your clients, by ControlPlane, by whoever, to see if they're reasonable guarantees or not. Okay? So formal methods are precisely that. And the way we work is we come up with mathematical models of the system, we come up with a mathematical model of the security properties, and then basically we generate automatically a search space that our tools are able to search, looking for attacks, or if they don't find attacks, then giving us the guarantees that we were talking about. Okay? Here are just some examples. I'm not going to dwell on them. Some examples of things that have been verified using formal methods. Mars, Pathfinder, and Curiosity Rover. I actually know some of the people who were involved there. Flight control software for Airbus and Boeing. At some point, many, many years ago, I was involved in a project trying to update the software of a plane while it is flying, which is quite cool, actually. And more or less it works. Depending on which flight. But anyway, compilers and everything, many underground systems have been formally verified. For instance, many of the unmanned underground systems, or even if you take the shuttle at Stansted Airport or everything, they've been formally verified. Okay? Now, this is essentially what we do, and this is relevant for you in general, not just for the work that we're doing, but essentially we start from a system. And the main effort, and this is where you need people like Mario or myself who have some Giuseppe, Mario and myself, is to come up with a formal model, right? So you need to take your system and come up with a mathematical model of the system. And then you add the security properties. And these security properties, they come from organization policies. So, and notice here that there is nothing about Kubernetes and there is nothing about the concrete work that we have been doing because this is just the standard workflow that we are considering. So starting from your policies, you come up with a mathematical model of the security properties. And then essentially, you play kind of a game. Okay? And the game is, can your formal model satisfy the security properties or not? Okay? And you do this via automated reasoning. And ultimately, what you get is either a violation trace, because you search a space, and if you find an attack, well, it is an attack, and you have a trace, which basically shows the steps of the attack or of the violation. Or you come up with a proof under certain guarantees in some cases, or in some cases, your tool will not terminate. And that's why we said nothing, because, as I said before, the attacker can always do something else, right? But in many cases, you will be sure, and there are results there, that if you have not found an attack within, let's say, half an hour or 1 hour, then you can be pretty sure that there is no attack. Okay? So there are a number of techniques that we can employ there. And notice that I'm talking about half an hour or 1 hour, but in most cases, it is actually seconds or milliseconds even. This is another way to show it, to show the same workflow. So we start with the system requirements, we come up with a formal model, we have the security properties, and here essentially we explore the entirety of the space, evaluating every possible permutation, and then we verify and we find a violation or not. Let me give you a concrete example. This is essentially what we're doing. We generate a search space, and this is generated mathematically, no formulas, but you can show that you start from an initial state and you generate a tree, or it can be more complex structure, it can be a graph, and basically you look for traces, for pathways in the search space that could lead to a violation of a security property. Let me give you a very, very quick example. I don't want to dwell on it. It's just an idea. But essentially, we could come up with a security property that says that a technician can override factory machine controls only during maintenance windows, and if authorized by a supervisor, and if the safety lockout procedure is logged and active. Okay. Now, take this property and rephrase it in your domain. There are a number of different solution. There are different ways of formulating it here. For instance, a certain transaction, if you're looking at finances, can only be operated, or a loan can only be given if a number of people have checked that the conditions are satisfied, if the markets are such that they allow them, and if there are certain guarantees in place, and so on. So essentially, what we do is we transform this mathematically, into a set of mathematical formulas, and we search our space. And here you could see, for instance, one pathway that would, the one in bold, that would indeed satisfy this property. Okay? Believe me, I mean, we haven't put the formulas there, so, this is just an example. But at the same time, there could be, and there are some interesting things with the colors, but anyway, this should be red. Or reddish. Yeah. Anyway, basically, this is a trace where the same property is violated. Okay. And here you can see the power of formal methods, right? Because if you had a human, first of all, as a human, you would need to think, okay, what is the tree that I'm searching? What is the search space? And maybe as a human, you forget something. That's okay. We all do that. Machines are much better than us at doing this. And then you have to search it, which again is very difficult for a human, even no matter how experienced you are. So machines are much better able to actually find the attack traces and the like. And that's all about formal methods.
Because I'm going to mention again.
Yes.
So again, bringing the whole thing back to your systems, the systems you operate and secure. Let's look at Kubernetes and, again, going beyond threat modeling to guarantee security assurance. So if you had a guess, what do you think this is? the hints are it is not a biological system, it is not a galaxy. Any guess?
Microservices?
Beyond that?
Service mesh.
Kind of. Mario.
I know, I cannot say. I
Tell
know
us.
what it is.
Tell us.
This is exactly all the dependents inside of a cluster of Kubernetes. So imagine when you call an API, these are all possible permutation or combination that you have inside of the code of the API. Look like stars, but they're not.
It is very complex. Kubernetes is a complex system indeed. So your Kubernetes deployments are very complex. So there are hundreds, if not thousands, of permutations in real-world clusters. And clusters tend to be more complicated than, for example, control systems, like in the example that we showed you before. You've got policies, role, namespaces, workloads running on top. And that's where the threat modeling limitation comes in, because it's really hard to understand what can go wrong. And what we do know, though, is the security properties that the system must preserve. So, for example, organizational policy, again, at corporate level can say systems must prevent users and applications from gaining high-level access unless it's approved and recorded. That security property can be translated, depending on the system you're hardening, in different ways. In Kubernetes could be, for example, a user mustn't be able to deploy a privileged pod. So what we do, applying formal verification for the cluster. The prototype we are building after Mario took care of formalizing Kubernetes in a way that can be, again, fed into an automated reasoner, is exactly that. Returning one or more violation trace based on this system state space exploration that Professor Viganò mentioned. And that is, if something is returned, that is a verified threat. That's not hypothetical. And most times is enabled by a toxic combination of configurations of different components across the whole cluster. And that's the trace that returns. Now, as good threat modelers, what we do, we want to keep your system safe. So we derive security control. And applying a security control, that's when we make that state that the tool returned not reachable anymore. So we have mathematical proof, can I say that? Yep. That the state of insecurity is not reachable anymore, aka the attack is not possible anymore. That's how it works in a nutshell.
Maybe another way of saying it is that once you have the attack trace, you know what are the steps that lead to the attack, and therefore you can intervene in blocking one or more of these steps, which is exactly what is shown there and what you said.
Exactly. Again, a couple of other examples. You'll find them in the slides we will share. Other properties that we want to make sure they are guaranteed by our deployment. I'll just take one. Can it ever become true that a privileged pod exists in this namespace, even if none exist right now, and only limited scoped permissions are granted today? And the prototype will also analyze the permission. So it's a very comprehensive, a cohesive view of the entire cluster configuration and state. Super, we are almost at time. So again, threat modeling, derived controls, supported by the prototype we are building. But unfortunately, math, I remember, trust me, math can be really hard to comprehend. So most times a trace consists of that you can see on the left. So what the prototype is also doing to make it consumable, to make the output consumable by human beings, of course we are using AI, yes we are. And that component in our system translates a trace coming from the reasoner into something that a human can comprehend. So in your cluster, the way it's configured, this security property is not guaranteed because of these conditions. And you should introduce these controls to secure the cluster. Now, the controls can come from any standard. Of course, at open source in Finance Forum, we want to mention CCC. We are heavily involved in CCC. Kubernetes is not covered yet, but it will be soon. For those of you who don't know, CCC initiative within FINOS, cross-framework mapping real-world controls, tech agnostic, but then individual controls can be made platform specific, so there will be control specific for Kubernetes. If you want to use NIST, by all means, all these standards, they map to each other, so you can demonstrate the security baseline you implemented across many standards. And with that, that's the URL to the repository. You're all member organizations of FINOS, so you can access and contribute to it. Please do so. And with that?
That's me. So, one of the key takeaways is formal methods can make a difference. Now, they're not a silver bullet, right? So it's not that we have solved all the problems, because in many cases, as I told you, it's actually difficult to come up with a mathematical model. It's difficult to model the properties, and your tool might not terminate. But they can help, and they can find attacks that humans are not able to find. So they are a silver bullet, but not everything out there is a werewolf. There are also vampires. Vampires are not killed by silver bullets. Okay? But there is a price to pay, and this is where the partnership, academia, and industry really pays off. Okay? Because there are additional efforts, as I was saying. There are additional efforts in terms of expertise. It's not easy, for instance, for a company to actually hire formal methodists, so people like Mario and myself. So this is where partnerships like KTPs or other form of partnerships can really help, because you bring together people with common desires and different knowledge, and you can really work together. Okay? And the good news is that Kubernetes can be truly hardened using formal methods. Okay? So we have not yet published about this because we have a prototype, but we are in the process of writing up all the results, which will be relevant not just for an academic publication, but also for an industrial publication, and we will have white papers and the like. So essentially, let me terminate by saying, they can make a difference. There is some investment to be made, but it pays off really, really well. We hope to convince you with the papers and the results more concretely in the future, but we also want to finish with a call to action. So reach out to us to learn more. You can reach out to ControlPlane, you can reach out to me. We'll be very happy to tell you more about the project, and also very happy to talk more generally about the importance of formal methods in a cybersecurity context, especially in the finance context. Thank you.
If I may add the last thing, very soon the tool stack will be, at least in its beta state, will be production worthy, at least consuming actual real-world cluster APIs. So we will definitely reach out to ask for the first use cases, and start stress testing the stack and see what it returns. And the mutual benefit is that you'll start getting some of that intel we can provide through that prototype. All right? So that's us done. Thank you so much for listening.
Thank you.